E já tem muito tempo ali na USP?
Já, na verdade eu fiquei um tempo lá no IPEM, né? Fiquei um ano e meio no IPEM. Eu era da USP, eu fiz a graduação, doutorado e um pós-doc, aí eu fui lá pro Lugão, que eu fiquei no IPEM um ano e meio, depois eu voltei para cá e tô lá aqui desde, desde então. Na verdade foi um ano e meio, né, que eu fiquei só lá.
Acho que a gente coincidiu só uns meses,
Pois é.
não lembro. Só que eu
Eu
encontrei
acho que
você, é,
sim.
eu encontrei você por causa do Giovanni, o menino, acho que ele está na sala também.
Tá, ele foi inclusive fazer o doutorado no laboratório que eu fazia pós-doc antes,
Hum.
o que eu indiquei ele. Ele,
Disculpen, ¿están
sí,
conscientes
sí.
de que estamos transmitiendo en vivo a través de redes sociales también?
Sí,
Ok,
No,
todo
nada
bien.
importa.
No sé si hay
no,
problema, pero es
no.
una conversación personal, pero no hay nada secreto.
Sí, sí, así es, sí. Empecé a escuchar datos y dije, bueno, estamos en
Sí, sí,
redes sociales.
sí, sí.
En unos minutos más. Gracias. Estamos en tiempo, doctora.
Buenas tardes a todos. Vamos a iniciar con nuestra siguiente plática de nuestro simposio. En esta ocasión tenemos al doctor Jonathan Dulival dos Santos. Déjenme hablarles un poco de él. Bueno, voy a decir su reseña en inglés. Dr. Dulival, he holds a bachelor's degree in environmental chemistry from the Institute of Chemistry of the University of Sao Paulo and PhD in Science Chemistry for the University of Sao Paulo in 1913. He is currently a researcher at the Heart Institute of the Faculty of Medicine and the University of Sao Paulo, where he develops vaccines with nanoparticle currents. He has experience in the area of inorganic chemistry, an emphasis on nanomaterials and surface-enhanced Raman spectroscopy, having a row of 30 scientific publications and patents. Thank you once again, Dr. Jonathan, and you may begin wherever you are ready.
Gracias, muchas gracias por la invitación, por participar del evento. Especialmente gracias a Mayele por invitar y al comité organizador. Podría intentar hablar en español, pero me siento confortable en hablar en inglés. Pero si hay preguntas al final, pueden ser hechas en español o en inglés, como quieren. Yo voy a cambiar ahora para inglés, pero thank you very much for the opportunity. Hope you guys be enjoying the event. The topics are very interesting. Looks very interesting. As Majali told you, I'm working in the University of São Paulo. I'm working specifically in Institute of Chemistry, but I have collaboration with the Institute of Heart of the University of São Paulo and Faculty of Medicine. Today I will talk about the plasmonic nanoparticle synthesis properties and the application of these nanoparticles more related to medicine. So the summary of my presentation is this. I will talk a little bit about the importance of gold and silver nanoparticles. So I will talk a little bit introduction of surface plasma resonance. That's the phenomenon more interesting related to the gold nanoparticles. So I'll talk about the synthesis and application and conclusions. But first, I would like to talk a little bit about Brazil. Brazil, it's very beautiful. There's a lot of natural wonders, like Mexico. But I would like to talk about the maybe three more beauty if you don't know. But you have the Amazon River. Amazon River is the biggest river and flow of water in the world. You have Iguaçu Falls. They are very beautiful. Also, I think more beautiful than Niagara Falls and Copacabana Beach. So if you come to Brazil, there's three important points you should see. But I'm not from any of these places. I'm from São Paulo. São Paulo is a big city. It's the biggest city in America. It's even bigger than Ciudad del México and bigger than New York City. It's a very important city in Brazil. It's 10% of the economy depends on this city in the country. So you have a lot of culture, diversity. You have Portuguese, Italians, Japanese. You have a lot of people from South America also. And this is a view of pointer. Yeah, here's the view of the university, and this is the Institute of Chemistry here. And here is the Faculty of Pharmacy and Chemical Engineering. This is the view of the entire campus, and this is the center of the campus. But let's do the presentation. What about gold or silvers? Gold and silver, it's very important along of history. You have recorded the people, that's a picture from the movie, but since the shores of Persia, you have a lot of people using gold and silver as symbol of power. Here, also more modern forms of power is like the famous people. This is a rapper from India, and this is the Gisele Bündchen International Brazilian model. But talking about specifically nanoparticles, you have reports people producing nanoparticles since 4th century before Christ. So that's the Lycurgus cup. And if you illuminate this cup from outside, you see a color of green. But when you illuminate, you put the light inside the cup, you see the color changing to red. And this red are gold nanoparticles. And when you see the light from outside, you see the silver nanoparticles. And more impressive, the people since this time was able to produce nanoparticles and put in glass. So this is the window in a church in Europe. That you can see the red are specifically gold nanoparticles. But why is that possible? Why, in general, when you see gold, it always yellow, but in this case is red. Where does this color come from? Well, this color comes from specifically from a phenomenon called surface plasmon resonance, and the name comes from the plasma. The plasma is a property when you apply a difference of potential in a gas phase, you are able to free the electrons in the gas. This collective oscillation usually called as plasma. This phenomenon can be also be seen in the surface of a metal, but this oscillation is not related free in the gas, but free in the surface of this metal. And when you put a light with that have the same energy of these electrons in resonance, we usually call this a surface plasmon resonance. And trying to illustrate this more like a visual way, you can see this as a light interacting with a nanoparticle. And when this energy of this light, this wavelength, match with the energy of these electrons in the surface, you have a resonance that change the position of the electrons in the surface. So that's what you call resonance. So you can move the charge in the surface of the nanoparticles. This movement change with the size of this nanoparticle, change with the size, the composition, and the form. You'll see more a little bit in the next slides. But this phenomenon can be seen also in the surface. So you can get in resonance in a metallic surface. This movement of charge in the surface is very interesting, and usually you can see this phenomenon applied to surfacing Raman spectroscopy. Raman spectroscopy is a vibrational spectroscopy, if you can see the vibrational modes of molecules in the surface, and you can increase the sensibility of this technique several times, like 1 million or more times, just putting the molecules in the surface and apply or incident wavelength or illuminate with a laser, for example, which the have the same energy of these electrons. Well, but I think the point is why you should study nanoparticles. Nanoparticles for itself are very interesting. If you think just in the possibilities related to the synthetic method or the particle synthesis, you have a lot of possibilities. In this case here, you are just seeing the color change just by changing the size of nanoparticles. If you increase the size, you can go from the yellow to the red, but you can also change the color of these nanoparticles, change the form. So if you have like HOTS, you produce blue nanoparticles or green nanoparticles, just changing the size of these rods. But you can also change the colors, the color of the nanoparticles. If you produce, for example, triangles or pyramidi, you can produce very different colors. In this case, we are seeing silver nanoparticles. And plasmonics can be applied in very different areas. In this case, I talk about sensing. Sensing is very interesting. So you can detect molecules in the surface of the nanoparticle or molecules in the surface of a nanometric film. You can use the sensing to detect a disease, for example. You can also use this as a substrate in spectroscopy. As I told you, you can use as a substrate to run a spectroscopy. So you can increase sensibility to detect a pollutant. For example, you can detect toxic species in water just using like heavy metals or hormones just to using nanoparticles. But you can use also nanoparticles in theranostics. So you can put these nanoparticles, for example, in rats, just to make how they can use to control disease, for example, cancer. I'll give more examples in the next slides. But let's talk a little bit about the synthesis of plasmonic nanoparticles. In general, you can resume a synthetic procedure like you have a salt metal or a metallic salt, and this metal is reduced by different molecules and generate the nanoparticles. So these metals, if you are thinking to produce plasmonic nanoparticles, you usually see these metals like gold, platinum, silver, palladium, copper. But if you are more interested to produce nanoparticles with colors in the visible, you always you use silver and gold and copper. But Lamer tried to put a mechanism to how to generate nanoparticles in solution. In general, when you have if you want to produce nanoparticles, you initiate with the salt. So in solution, the salt you generate monomers, and those monomers you grow and generate a nuclei, or this is your part of nucleation. In this part is a critical part that after you generate the nucleation or the nuclei, you can grow these nanoparticles to generate, for example, spheres or spherical nanoparticles. But if you change the medium, or if you have species like surfactants or polymers in solution, you can change this path and in generating not only spherical nanoparticles, but you can generate like spheres or rods. This is a very important field of research. So you can expand your entire life just looking how change the reactants to produce this nanoparticle, and how can you make this even more interesting. This is an example made by Mirkin and collaborators. Mirkin is very important professor in the area that he expanded his research just to produce nanoparticles like this, where you can, for example, in this case, he and his group just show how you can change the forms of the nanoparticles and modifying the corner, the edge, or the face of the nuclei or the other nanoparticles. So you can produce very different, because you change the kinetic and you change the energy of in the synthesis. So after you control this possibility, you can produce very different forms. For example, icosahedron, cube, in other forms very, very different that I even don't know the name of these forms, but you can produce, you can just spend a lot of time just changing and studying how to produce these nanoparticles. And there are a lot of forms to control these nanoparticles. You can control, for example, just the average size, controlling the concentration of the reductant, the starting rate, the temperature. So you have a lot of forms to control. You can control the size distribution, basically change the same parameters, and you can change the stabilization, change the composition of the solution. So there's a lot of things to do with nanoparticles, just thinking about the syntactic procedure. So now I talk a little bit about the applications. The application, I think the one of the more interesting applications related with nanoparticles are to use to detect biomarkers in cells. So in this case here, the author just put nanoparticles in cells. You were able to detect the position of these nanoparticles. If you see, there are a lot of bright points here, and every bright point here is a nanoparticle. But how is that possible? Here is a bar with 5 micrometers. How is that possible to detect, I don't know, 50 nanometers nanoparticle? This is a very special microscopy called dark field microscopy. So you can detect these nanoparticles specifically in a point, because these nanoparticles, especially gold and silver nanoparticles, can be detected because they increase the signal just by increasing the scattering light. But you can also it's not just detect nanoparticles. You can detect, for example, the species inside the cells. In this case, in this example, the author first synthesized gold nanorods and try to use these rods to detect sulfide in solution. The first thing was to make the entire procedure in solution. And I think I didn't I didn't tell you yet about this thing here. This is the electronic spectrum of the hot rods. So if you have a color change, that means these nanoparticles has a change in the surface and the surface resonance plasma. So here's a typical electronic spectrum of the surface plasmon resonance of these rods. And when you modify these nanoparticles, you have a change in the surface plasmon, or you have a change in the electronic spectrum. And the author were able to detect and build a curve with the different concentration. And he did this in solution. And after this, it was possible to put this inside a cell and detect the sulfide inside the cells. In the same way, he was able to detect the concentration of sulfide in very different concentrations. But the point is, why should I detect sulfide inside cells? Sulfide is very important to cells. Sulfide is very important to modulation of the cellular respiration, regulation of vasodilatation, neuroprotection. There are a lot of things related to sulfide. So sulfide is very interesting. And sulfide has great affinity to gold. So it's very easy to detect in concentration of 1 nanomolar. Now I give you, I have like 10 minutes, but I try to give a brief example. This is my example. I have to publish this paper a couple years ago. That's you can produce an example that you can see from since the production of the nanoparticles until the application. This is an example of application of gold nanoparticles, but nanoparticles with radioactivity properties. Radiation or radioactive compounds are very interesting to cancer treatment. So you can use these nanoparticles, or you can use this material to the treatment of cancer. But there is a lot of challenges to produce this. You need first prepare these nanoparticles. You have to modify these nanoparticles to be specific to the type of cell, and then you have to characterize the damage of the radiation. So the first step was to produce the radioactive gold. So this is a facility here in São Paulo, inside of the University of São Paulo, but it belongs to IPEN, Institute of Research in Nuclear Energy. This is the point of view, the reactor. Here in the side view, you can see this bright blue light. This is the reactor. Yeah, the reactor reacting and producing the radioactive species. So after you put your sample here of gold, for example, you produce this radioactive species, and after this you have to characterize them. And if you did this right, you can see the gamma spectrum. You can see the energy of this spectrum. And I think there's a curiosity here that when you irradiate or when you produce radioactive gold, 198 gold, and this 198 decay to mercury. So in general, you can see you are producing, or you are generate crap from gold. That's a bad thing. But what's very interesting is the amount of the gold which generate mercury is very low. So you don't generate toxic species, but you can use this material to the medicine. So that's the procedure. I don't have much time to explain everything, but first time you have to, after you produce the radioactive gold, you have to oxidize. Then you remove, for example, you have to oxidize using aqua regia. So you remove the acid and then you reduce by the usually or the common methods, like this is the Turkovic method. And if you did this right, you can see a suspension of red nanoparticles, and in this case with 14 nanometers. After this, you have to modify. You can modify these nanoparticles, for example, with bovine serum albumin. And in this case, we modify these nanoparticles. Actually, in this case, we have produced nanoparticles in two different concentrations of radioactive atoms. In this case, it's like 100 or pure radioactive atoms. In this case, was to diluting with non-radioactive atoms. And they have basically the same spectrum. What make it very hard to see the difference between a pure radioactive sample from a part non-reactive sample, but you can use different techniques to detect this. As I told you, you can do Raman spectroscopy, and you can detect the damage caused by radioactive samples, measuring the radioactivity, measuring the spectroscopy or measuring the Raman spectrum. And as you can see, the intensity here are very different from a sample with part radioactive from a non-radioactive or a pure radioactive sample. But in general, Raman spectroscopy or surface enhanced Raman spectroscopy are not very analytical technique. It's not possible to detect this or quantify this. So, but you can use different techniques to quantify this. Another technique you can do is the fluorescence spectroscopy, and you can use, for example, the tryptophan component present in the bovine serum albumin to detect the damage of the radiation. So you can even quantify and compare to a sample irradiated with external source of gamma radiation. So you can quantify this damage, and you can apply this nanoparticles. This is not my paper. It's not exactly the point what I did, but you can apply these nanoparticles to the treatment of cancer cells, and you can see the control of the growth of the cancer cells. In this case was prostate cancer. So you can see the control of cells different. You can see the decreasing or not growth of the cancer cells. Here the control group that you can see the growing of the cancer cells. So there's a lot of applications involve gold. So I think it's hard to explain 25 minutes, but this is you can just to prepare the nanoparticles, you can apply these nanoparticles, and there are a lot of applications in gold. So thank you very much. This is the collaborators I'm having worked in the last years. So thank you very much. That's the financial support, the Brazilian adjacent support that paying everything. And thank you very much. Gracias por su atención. Estoy abierto a preguntas.
Muchas gracias, doctor Jonathan. Si alguien tiene alguna pregunta, puede abrir su micrófono o puede colocarla en el chat. Ok, en lo que escriben las preguntas. Ok, tenemos aquí una pregunta de María Guadalupe. Adelante, puedes abrir tu micrófono. Y también Giovanni Morcelli, ¿puedes abrir tu micrófono?
Hello, do you listen to me?
Sí.
Yes, yes.
Okay, I will do my question in English because it's easier for me than in Spanish. So thank you for this presentation, Jonathan. Very interesting. And I would like to ask about the specificity of, I'm considering this example that you gave about the detection of sulfide in cells, right? I would like to ask about the specificity. So, and also in a more broad context, how specific can be the applications of gold nanoparticles for the detection of a specific molecule, or is just more like the detection of any molecule that has like a sulfide moiety or something like this? I don't know if
Yeah,
I was
no. Okay. Thank you, Giovanni. In this specific case, it is not very specific. So, as probably you know, the gold has affinity very, very big to sulfur. So, I believe the author did not try to detect specifically, but he tried just to show a concept to how to use gold nanoparticles in that case to detect inside or to detect a change inside the cells. I don't know exactly how they did this, but he increased the concentration inside the cells. He just saw the changing in the spectra of the gold nanorods. So this is probably not the best example if you want to detect something specific, because they are just using the shift in the plasma band. But if you want to detect something very specific or do something more or if you want to do something very specific, you probably should use Raman spectroscopy or surface enhanced Raman spectroscopy. I don't know if I answered a question, but that's why I think about this article in particular. It's
Yes,
not
yes.
the best example for specific, but it's interesting in a form to prove a concept.
Of course. Well, thank you. I don't know if I could ask just another question about how is the field going. There is already some reliable methods already being applied, like for the detection in cells or in some real system.
I didn't get the beginning of your question.
Oh, sorry.
Can you
So
repeat?
it's more, yeah, it's more of a it's more like how is the advancements of the field going? There is already some reliable methods being used to detect, to quantify some compounds, some assay, something like this.
Yeah, that's, how can I say that? But the people use a lot of gold nanoparticles in assays to detect especially disease, but outside of cells. When you go to inside of cells, I think there are a lot of problems related to how to detect the position of the nanoparticles. As I told you in the presentation, if you have equipment like a dark field microscopy, you can see and you can look where are these nanoparticles. But when you don't have, it's pretty hard, because I think the problem related to use dark field microscopy is not very cheap technique, so it's not easy to turn this available to the population, for example. and available to any lab which want to develop this. But in the case of assays related to outside of cells or using blood, there's a lot of things developing. Actually, most of the assays involve nanoparticles are related with color change. So that pregnancy test and the COVID-19 test, that strip use like red colors, they are nanoparticles. So there are a lot of things being developed, but they are more outside cells, and they usually like saliva and blood. So that's more common. But there are a lot of things. The development related to cells, it's a little bit limited, but outside cells is very common.
Nice, thank you. I didn't know about the COVID test. Very nice. Thanks.
Y tenemos una pregunta en línea. Ok, dice, ¿cuáles son los principales parámetros que determinan la forma o la estructura de las nanopartículas?
I answer in English. I think it is familiar, but there's a lot of parameters. That's one thing. I cannot say just, as I told you, is if you are using a different salt of metal, if you are using temperature, you can control, for example, how big or how small are the nanoparticles. If you use, for example, a surfactant, you can control the shape of nanoparticle. If you are first doing a seed, I mean, if you are just growing very small nanoparticles and then you put these seeds in a different solution, you can control the shape, so you can control also the form and the size. So there's a lot of things. It's not easy just to say one or how many. You can control since the temperature or the medium, if you are doing the synthesis and alcohol, or if you are doing this in water, you see very different forms, you see very different size. So there's a lot of things. I think if you are interested in produce, or if you're interested in synthesize, you can look, for example, the Chad Mirkin group. You see a lot of how they produce. I'm not a specialist to produce nanoparticles in anisotropic forms. Anisotropic, I mean, not different than spherical nanoparticles. Spherical nanoparticle is my specialty. So I specialize to produce spherical nanoparticles. So, but you can look this in literature, especially to the Mirkin group.
Ok, muchas gracias. ¿Me permite compartir pantalla, doctor Jonathan?
No.
Okay, thank you very much. Again, and SCAN 2024 extends its gratitude to Dr. Jonathan Solivar for his presentation, and we will also send you your participation certificate by email, and thank you again.
Gracias.
Ok, muchas gracias a todos. Los invitamos a pasar a las salas respectivas a su trabajo de póster para poder iniciar la sesión de póster. Muchas gracias.
Buenas tardes, ¿cómo pasamos a la sala 3?
Ok, mira, déjame terminar de compartir. En la parte de abajo del Zoom vas a encontrar una unos cuadritos que dicen que entrar a las salas. Ahí vas a encontrar el número de sala y tienes que entrar a la sala 3. ¿Sí lo encontraste?
Unos cuadritos.
Sí, son 4 cuadritos. Ahí puedes entrar.
No veo los cuadritos. No, no los veo.
Con gusto te puedo enviar, Yarelis. ¿Sala qué dijiste?
Sala 3.
Muy bien. Jacobo, ¿tienes algún detalle? ¿Alguna pregunta?
Sí, me gustaría, tampoco encuentro los cuadritos para entrar a la sala 4.
Muy bien, Jacobo. ¿Pueden escribirlo en el chat para hacerlo un poco más rápido?
Sí, claro.
Sí, yo aquí ya te voy a asignar, Jacobo. Gracias. María José Alves, a la 3.
Por favor, a mí también me puede asignar
Sí. Diana, ¿cuál sala?
sala 1. No me aparecen los cuadritos.
Bien. Salinas, sala
A la 1,
4.
por favor.
Sí, un momento, un momento. Salinas, sala 4. Ya se fue. ¿Quién dijo la 1? ¿Giovanni? No. Giovanni a la 1.
Diana.
Para quienes están ingresando, bienvenidos al Simposio de Química Aplicada a Materiales Plásticos. Simposio de Química Aplicada a Materiales. En su pantalla, ustedes pueden visualizar las sesiones de póster. Pueden dirigirse a través de la herramienta del Zoom, salas pequeñas. Entonces, ustedes ahí le dan clic, es un cuadrito que está en su barra de herramientas del Zoom, y seleccionan el número de sala. Acá. Un momento. Si acaso ustedes no pueden visualizar ahí el número de salas, estamos en este. Sala 1, aplicaciones de energía. Sala 2, aplicaciones de energía también. 3, materiales para el tratamiento de agua. y materiales para el tratamiento de agua. En caso de que no puedan dirigirse, por favor, en el chat me mencionan a qué sala y yo los puedo cambiar con gusto. Salo, a ver, aquí. María José, creo que ya lo habíamos movido, sí. Gonzalo de León, sala 2. Ya se fue. Jessica, sala 3. Ya se fue también. Muy bien. Ángel, sala 1. Quienes acaban de llegar, les recuerdo, estamos en el Simposio de Química Aplicada a Materiales. Andrés Gabriel, sala 2. Listo. Muy bien, entonces en el Simposio de Química Aplicada a Materiales. En este momento, Erika, muchas gracias. Muchas gracias. En este momento estamos realizando la sesión de pósters y hay 5 salas. Ahorita es la sesión un poco más pesada, tenemos 5 salas. Sala 1, aplicaciones en energía. Sala 2, también aplicaciones en energía. Revisen por favor cuál es el folio del trabajo que a ustedes les interesa. Incluso pueden entrar a una sala y luego después entrar a otra. Sala 2 y 1, aplicaciones en energía. Sala 3, materiales para tratamiento de agua. Sala 4, también materiales para tratamiento de agua, al igual que sala 5. Nos están preguntando del programa de carteles. Entonces déjenme ver y poder colocarlo aquí en en el mismo chat. Aquí está. Muy bien, en el chat, ahí encontrarán el programa de carteles, de pósters. Ya detallado, ese programa tiene cuáles son los nombres de las exposiciones que tocan en cada sala. Muy bien, les recordamos, estamos en el Simposio de Química Aplicada a Materiales. En este momento tenemos 5 salas en sesiones de póster. Buenas tardes a quienes van ingresando. Nos encontramos en el Simposio de Química Aplicada a Materiales. En este momento estamos realizando la sesión de pósters. Tenemos 5 salas activas, 2 de aplicaciones en energía y 3 de materiales para tratamiento de agua y residuos sólidos. Para ingresar a cada sala pueden seleccionar en sus opciones de herramientas de Zoom, ¿sí? En la barrita, ahí donde están los botones, cuál es la sala de su interés e ingresar en ella. En caso de que por alguna razón no tengan ese acceso o se les complique, en el chat escriban por favor el número de sala y los moveremos. Muchas gracias. A quien acaba de ingresar, muy buenas tardes. Estamos en el Simposio de Química Aplicada a Materiales. Estamos en las sesiones. Ay, Jessica. Jessica, marcas que requieres ir a la sala 5. Vamos a ver.
Bien, tenemos algunos participantes que ya están asignados a la sala. Necesitamos que den clic en entrar, por favor. En donde aparece el círculo con los 3 puntos suspensivos, van a encontrar la opción de ver salas para grupos pequeños, que es un panel con 4 cuadros más pequeños. Entonces, si dan clic ahí, por favor, les va a permitir entrar.
María José, Montserrat, Carla, ya están asignadas a las diferentes salas. Solo nos aparece que no han seleccionado la opción de entrar.
Gracias, doctora.